Richard James will present Transposition Tutorial 3. Because of the two fractions that contain the proposed subject in the denominator, we could have taken an approach in which those fractions are placed together on one side. However, I always opt to eliminate the denominator when the alternative is about as difficult or maybe a bit more challenging. So we have right here S is the proposed subject, and we have it present in the denominator of those two fractions. We have two choices. One, eliminate the denominators immediately, or two, place these two fractions on the same side. That is, the two fractions that contain the proposed subject. I am saying I usually opt to eliminate the denominator when the alternative is about at the same level of difficulty, or maybe a little bit more challenging. There is no doubt that the difficulty is not with the logic of the problem. The difficulty will be with how cumbersome the expression is, and I am opting to go with the one that is less cumbersome, and that I achieve by eliminating the denominators. An early step to flatten an equation has the potential to make expressions less cumbersome and maybe less complicated. We will therefore eliminate the denominator by multiplying the entire equation by S, and I'm saying I'm going for less cumbersome. In the end, we will take a look at the alternative, that is, uniting the two fractions that contain the proposed subject. Therefore, after eliminating the denominators, we will take a go at the problem again using the other method. But of course, in an examination, a candidate should not really attempt to use more than a single method in solving a problem, because you will not get any extra mark for having two occurrences of the correct solution. So your decision should be one that is guided by time, effort, and also space. First, we will eliminate the denominators by multiplying by S. So there we have the entire equation being multiplied by S. The entire equation being multiplied by S, we take the first fraction that we have here, multiply that by S. What do we know? We will have S cancelled with S, and the result is P over 1. Any number divided by 1 is equal to that same number. And the same will follow for the other fraction. No different. The S's are eliminated, and Q divided by 1 is Q. What about the other term that we have right there? With no denominator to cancel, it is just RS. R multiplied by S. Then we may put those together so that we can see that a little bit closer, and also do not forget the equal and addition signs. Eliminate Q from the right hand side by subtracting Q from both sides. We intend to make S the subject of the formula, therefore we need to eliminate this Q. this Q is the one that is least related to the proposed subject, and we eliminate that Q first. As a matter of fact, we need to eliminate Q and we need to eliminate R. And we are guided by the principle that when we have a number of terms, expressions, operations to eliminate, we eliminate the one that is least related to the proposed subject first. Q is least related to the proposed subject, therefore we will go straight ahead and eliminate Q, subtracting Q on this right hand side, and also keep the equation balanced by subtracting Q on the other side also. By so doing, Q will be eliminated from that right hand side, and on the left hand side we have P minus Q. Finally, we will eliminate R. As a matter of fact, at this stage, R is the only symbol in the way of S being the proposed subject. At this stage, it is being multiplied. As a matter of fact, they are in a multiplication relationship. Therefore, to eliminate that R, we will have to use the opposite of multiplication, which is division. Therefore, we will divide by R on that right hand side. But we have to do the same on the left to keep the equation balanced. All that is in the way of S being the subject is that R that is multiplying on the right hand side. We will therefore eliminate R by dividing by R on both sides. There we have it. And what will happen? On the right hand side, we have the R's eliminated, and on the left hand side we have P minus Q over R is equal to S. Finally, reverse the equation in order to cause the proposed subject to become the subject. And that's all there is to it. Let us take a look at the steps involved in the approach in which the terms that contain S are placed together. We will do that without intermediate steps and also without much explanation on the other slide. Begin by placing the terms that contain the proposed subject on the left hand side. So we have the proposed subject is S. We have one occurrence of S on the left hand side, and we have another on the right hand side. In this first step, we will cause all of the terms that contain S to be accumulated on the left hand side, and of course we will do that by subtracting the fraction Q over S from the right hand side, and we will subtract the fraction Q over S on the left hand side. That will cause Q over S to be eliminated from the right hand side, and on the left hand side we have P over S minus Q over S. Find the difference between fractions that have the same denominator by finding the difference between the numerators. So the fractions have the same denominators. All we need to do, subtract the numerators and place that result over the common denominator. Let's go straight ahead and do that. That's all there is to it. And all we need to do is make R the subject by reversing the equation as we have it right there. Here we have two options. 1. Reciprocate R2 multiplied by S. So at this stage we are faced with two possibilities. As a matter of fact, we may consider that we have a lot, but I am just taking consideration of two of them. Here we have two options. One, we may reciprocate because S is the proposed subject and is in the denominator, and that is always a very good move to make when we have the proposed subject in the denominator. We may take the opportunity to find the reciprocal, especially when we do not have a lot of different terms. We have one fraction here and we have another. Well, this does not appear to be a fraction, but we know that it is, because this is a fraction that is equal to r over 1. So we may find the reciprocal of both of them. That is one choice that we have. The other one we have is to multiply by s, because we have a denominator of s here. If we multiply by s, we will be eliminating the denominator. So we have the choice of multiplying by s. However, we will choose to reciprocate because the other approach will require an additional step of reversing the formula in the end. So if we opt to eliminate by multiplying by s, it will turn out that s will end up on the right hand side, and we will prefer if the subject be on the left hand side. Therefore, we will take the approach that will cause the proposed subject to remain on the left hand side, and that is by finding the reciprocal. We may take advantage of the fact that if two fractions are equal and we invert them, then they are still equal. We may always take a step like that when the proposed subject is in the denominator of a fraction. So there we have the reciprocal. What do we do next? We will multiply by this denominator, eliminating p minus q from this left hand side, and on the right hand side we will have that fraction multiplied by p minus q. We may therefore finish up by multiplying by p minus q. There we have it. S is equal to p minus q over r. And of course, what we have done right there is that we have taken the steps to ensure that the proposed subject remains on the left hand side, as opposed to eliminating the denominator by multiplication, which will cause the proposed subject to end up on the right hand side. In the attempt to make m the subject, which is what we are doing in this particular case, we are making m the subject. In the attempt to make m the subject, we need to eliminate everything that is a hindrance, beginning with the one that is least related to it. First, cancel the square root operation by squaring both sides. And in this particular case, we are making m the subject of the formula. And we have that square root operation, we have the 3, we also have that 5 to eliminate. And I am saying that we will stick to principle, eliminating the one that is least related to the proposed subject first. We will therefore eliminate that square root operation. The opposite of square root is square. Therefore, we will eliminate that square root on the right hand side by squaring. But we cannot square one side alone. It is an equation. Therefore, we will have to square both sides to keep it balanced. And by so doing, we have L squared on the left hand side, and on the right hand side the square root is eliminated. We will eliminate both 3 and 5 in a single step. Eliminate the multiplier, which is 3, and the denominator, which is 5, simultaneously. How will we do that? We will cause the existence of a particular setup that will cancel the 5 and cancel the 3. Well, the only thing that will cancel this 5 is a 5 in the numerator, and the only thing that will cancel this 3 is a 3 in the denominator. Therefore, we will create a fraction with the 5 in the numerator and the 3 in the denominator that we will use to eliminate the 3 and the 5 from the right hand side, and we will also have to multiply that left hand side by that same fraction. The 5's are gone, the 3's are gone, and all that is left is for us to reverse the equation. However, it is for us to understand that we may rewrite this expression 5L squared over 3. Then we will reverse that expression, and that completes our transposition. What do we have here? A substitution problem escaped into our transposition tutorials. I am happy for that, because sometimes we get programmed by the fact that we are doing mathematics problem of a particular nature, and therefore anything else is an impossibility to us. But this time we will prove that it is not an impossibility, because we have right there another problem from another branch sneaking in. We will also capture that culprit and make light work of him. Let us solve it anyway. It is still mathematics. So a substitution problem escaped into our transposition tutorial. Let us solve it anyway. It is still mathematics. And anybody remember what we always do when we have a substitution problem? Well, I remember we always create a template that resembles the expression into which we need to substitute. So let's go. There is our template that mimics the expression into which we are substituting, and we will cause the A to go in the position of A, which is of course the value of A, to go into the position of A, which is right there. And I do not know which one we will do first, but I imagine that we will cause those B's to go and occupy the positions of B, -2, -2, and C is there and there. So we will do the same. Nice. With or without the brackets, we will still have -2 minus 3 is equal to -5. When we are adding numbers that have the same sign, the values are added and the answer will take the same sign as the numbers that we have added. And you can think of it as if you are going into the refrigerator to take out 2 M&Ms. They are very yummy, so you choose to take out another 3. Therefore, in all, you'd have taken 5 M&Ms. And there's no problem with the denominator. Multiplying a negative and a positive, the result is negative. When we multiply 2 numbers that have different signs, the answer is negative. So there we have now 4 times a negative 5 all over negative 6, and we will reduce by a common factor of 2. 2 into 4 is 2. 2 into 6 is 3. And we will say 2 times negative 5 is equal to negative 10, and in the end we will say a negative 10 divided by a negative 3 will give a positive. Negative divided by negative is equal to positive. The rule that applies to multiplication also applies to division. Therefore, if we are multiplying 2 numbers and they have the same sign, the answer is positive. And in a quotient, if we are dividing 2 numbers and they have the same sign, the answer is positive. Here we have a problem that is similar but simpler than some that we have solved before. And maybe I'm saying it is simpler because we have the proposed subject on opposite sides of this equation, but we did not have to cause them to be there by having denominators. So this one is a quote-unquote flat equation already, and that is why I consider it to be simpler than the ones before. I consider it to be similar also because we have solved the problems in which we have the proposed subject on opposite sides of the equation. So here we have a problem that is similar but simpler than some that we have solved before. We will transpose that term on the left hand side that has the proposed subject to the right hand side, where it may be with the other one. And why are we transposing the term that contains the proposed subject to the right hand side rather than the left hand side, when in fact our intention is to get it on the left hand side eventually? Well, we are doing that because if we did the opposite, which is to the left hand side, then we will end up with 3 negative terms. Of course, if we have 3 negative terms, we may multiply an entire equation by a negative 1. If we multiply an entire equation by a particular value, it does not change the equation, just its appearance. So we could have done that. But in mathematics, there are 3 things that you do not introduce if they are not necessary: unnecessary negative signs, unnecessary brackets, and unnecessary fractions. And we will take the opportunity to avoid introducing unnecessary negative signs by transposing this negative 3t to the right hand side, and that we will do by adding 3t. we have to do that to both sides. So on the left hand side, 3t is eliminated, and on the right hand side we have RT plus 3t, and we always know what to do here. We have two occurrences of the proposed subject, and there can only be one subject. Therefore, we will factorize, making the proposed subject the common factor. Then we will divide by what we call the large factor. But how do we factorize? Factorization is the process by which we take the highest common factor of the terms and divide each one by the highest common factor. So let us factorize by taking a common factor of t, then divide each term by the common factor. There we have it. The common factor is here, and we are dividing each term by the common factor. Those are gone, and also that. So we have in this bracket 3 plus r. Let us eliminate that large factor by dividing by 3 plus r on both sides. Eliminate that large factor by dividing by 3 plus r on both sides. That's what we always do. As soon as we factorize, making the proposed subject the common factor, we divide by the other factor. And we eventually have to turn or reverse that equation. Write the new subject on the left hand side. If there is a particular operation, action, activity that works in a particular circumstance, we can take it for granted, or if not for granted, take advantage of the fact that we can do the same thing under the exact same circumstance. And if we have two occurrences of the proposed subject, we will factorize, and after factorization we divide by the other factor. And in this particular case, the proposed subject is on the right hand side. We just reverse, and that we may do under all such circumstances. After making t the subject of the formula, we are given values of r and s, and we are required to find a corresponding value for t. So this is another problem that requires us to substitute, and we will begin by creating a template. That is how it is with mathematics. When you imagine that you are finished with a topic forever, it turns up to haunt you. Some people even go as far as finishing with the entire subject, only to find it necessary a few years later. Let us see if we remember anything from our tutorials on substitution. Of course, yes, we remember. Create the template, that's first. Then we will just insert those values into the template, and the result is very simple. 15 divided by the sum of these two, so 15 divided by 5, that is equal to 3. The rest of the steps are self-explanatory, unless we cannot add 2 and 3, nor divide 5 into 15. And 15 divided by 5 is equal to 3. Here we have two choices. 1. Expand the brackets. 2. Transpose the fraction. We will opt to transpose the fraction, and we will eliminate both numerator and denominator simultaneously. Well, if we expand the brackets, we will have a fraction here, 5 over 9 times f, and we will have another fraction here. I am choosing to have less fractions in my expression by eliminating this fraction from this side. And remember that it's very simple to eliminate a fraction. We need to multiply by another fraction that will cancel the 9 and also cancel the 5. Therefore, we will have to use one with 9 in the numerator and 5 in the denominator, and we will do the same on the other side. And there we have it. The 5's are gone also, and on the left hand side we are multiplying. So we have 9c over 5 if we prefer to write it like that. And all that we have to do there is eliminate that negative 32, and we will do that by adding 32 to the right hand side to eliminate that negative 32, but keep the equation balanced by adding 32 to the other side. Lovely. Those are gone, and we have 32 left on that left hand side, and we will reverse the expression, writing the proposed subject on the left hand side. We will finish up with another substitution, because we also need to find the value of f when c is equal to 15, and there we have our template into which we will substitute. Here we go again with another substitution extension to the problem. We do not have to be boastful, just show that we are already experts at it. So just show that we are experts on substitution by creating our templates and also inserting the value, and finish up usually by simplifying the expression. Reduce by a common factor of 5. 5 into 15 is 3, and 5 into 5 is 1. We do not need to mention it. Then what do we know? 9 times 3 is equal to 27, and 27 plus 32 is equal to 59, and 59 degrees Fahrenheit. As a matter of fact, this expression that we have here is the expression that converts Fahrenheit, degrees Fahrenheit, to degrees Celsius. And that is how useful mathematics is. In the end, what you have done is that you have transposed this expression, arriving at one that will convert Celsius to Fahrenheit. And you did not do that only, but you actually found a corresponding Fahrenheit representation or value of a given Celsius temperature. And that is a great feat that you have completed, and you have done that by using mathematical principles. So we see that that is very applicable to everyday life. It is for us to remember that what we are actually doing is demonstrating especially the intermediate steps that we would have used in solving the problems. Here we do not have them. As a matter of fact, I have chosen to eliminate those intermediate steps almost entirely from the script. And that is what will be expected of candidates in the examination. You therefore do not need to demonstrate how, as we have done, these fractions are multiplied by s in great detail. You just need to write down the result. Therefore, you say p over s times s, this is the result, q over s times s, that is the result, and r times s, that is the result. You need to show that you are actually eliminating the denominator by multiplying by s, and you have done that. That is important. Here, what we are doing with this resulting expression, we are demonstrating without including the intermediate steps that we are making s the subject of the formula, and we need to eliminate this q that is least related to it. You will eliminate that q by subtraction, but you did not demonstrate that you are subtracting q from both sides. But this step is an indication that you have subtracted q from both sides, because by so doing, q is eliminated from the right hand side, and on the left hand side we have p minus q. Therefore, in your expressions that you are using in the examination, you do not have to include that intermediate step that is subtracting q from both sides, because this step is an irrefutable proof that you are sure that you understand that that is the process that is necessary. Also, after eliminating that q, you need to eliminate this r. You will eliminate this r by division, because it is being multiplied by s. But you cannot just divide by r on the right hand side alone. You have to divide by r on the left hand side also. By so doing, r is eliminated from the right hand side by division, and on the left hand side you have p minus q over r. Just writing this term here, just writing this expression here in this form is a demonstration of that fact, and it is not completely necessary to show every single step. So right here, all of the processes are assumed, they are understood, and they are portrayed, namely implicitly, but there is no doubt that all of the processes are there and they are correct. Therefore, you do not have to demonstrate with those intermediate steps. But in these tutorials, I am explaining every single one of them. In the attempt to make m the subject, we need to eliminate everything that is a hindrance, beginning with the one that is least related to it. First, cancel that square root operation by squaring both sides, and we have done that on few occasions. And what will happen? The square root will be eliminated from the right hand side by squaring, and we also have to square that left hand side where the square remains. And in the way of m being the subject, we have 5, 12, n, all of which may be eliminated simultaneously by multiplying by the appropriate fraction. So what fraction can you multiply that by in order to eliminate the 5, the 12, and the n? Of course, you will just multiply by a fraction that has 12 and n in the numerator and one that has 5 in the denominator, so that the cancelling is possible. But you have to multiply by that fraction on the other side also. So you have 12 is gone, we find the 5 is out, and the n. So we have taking the 12 as the coefficient, then taking the letters in alphabetical order, the n before the t squared, all of that over 5, and that is equal to m, and we will reverse the equation in order that the proposed subject will be on the left hand side. This is the last problem, and by now we should naturally eliminate the denominator by multiplying by p minus 3. We are also accustomed to multiplying on the other side without using brackets. So we understand that we need to multiply by q minus 3 in order to eliminate this denominator of q minus 3. Right. And we also understand that if we are multiplying q minus 3 on this left hand side, we will have to multiply r by q and negative 3 by r. So r, q, and r times negative 3, negative 3r. So there we have it. qr minus 3r and the q minus 3. We have that eliminated from the right hand side. And what do we do next? Making q the subject, we need to eliminate this negative 3r by adding 3r. And we will do that to the other side. So those 3r terms are gone. And all that we have in our way of q becoming the subject is that r, and it is in a multiplication relationship. Therefore, we will divide. So all that remains is for us to eliminate r by division. And what will happen? Those are gone, and on the right hand side we have that lovely expression. With q already on that left hand side, there is no need to reverse the equation. But what do we know? Immediately as some students see the square, which is the p squared, they start to find the square root. The fact of the matter is that the square is not interfering with the proposed subject. We are required to make q the subject of the formula and need to eliminate all obstacles in the way of the nominee becoming the subject. In this particular case, the square operation is not one such obstacle. Right, so the square operation that we have right here belongs to p, and we are attempting to make q the subject of the formula. Therefore, that square is not interfering in any way with our proposed subject. Therefore, we do not have to consider the square root at any single time. We are finished with the problems that we intend to solve in these tutorials. However, we have made some claims that may be quite credible, and I know that some candidates may not bother to question them because they are made by Richard James. Nevertheless, I am not one to leave claims without proofs. The first one that we will take a look at is the reason why we cannot immediately find the reciprocal of the fractions when we have two fractions on one side of the equation and one on the other. So if we have this situation, we cannot immediately invert these fractions because we actually intend to invert in order to make t the subject. And it is easier if t is a part of the numerator. So inverting or finding the reciprocal may be an objective in our mind. But we cannot do that immediately because we do not have a single fraction here. That is what I am saying. And let us see why we cannot do that. Therefore, in the quest to make t the subject of the formula, it is good if we had t in the numerator of the fraction. We may do that by reciprocation. We are, however, saying that we cannot do that immediately. We have to have only two fractions, one on either side of the equation. So we cannot immediately reciprocate. We have to have one fraction on the left hand side and only one on the right hand side. What is that? There we have what we consider to be the correct answer, which is actually the correct answer. It was found by adding the fractions first, and I'm just using this occurrence of it right here as a reminder, so we remember what the correct answer should be. It was found by adding the fractions first, then reciprocating after, which we consider to be the correct thing to do. On the next slide, we will take the reciprocal of all of the fractions first, then proceed to make t the subject of the formula and proceed to make some other investigation. So we will do the wrong thing and see if we get the result. Well, we will not get the correct result, but we are just demonstrating the reason why we have to have one fraction on the left and one on the right. Therefore, we need, before we can reciprocate, to have these fractions added to form only one fraction. And we will take a look at the alternative, which is to do the reciprocal before adding and see what happens. Let us do the reciprocal first, then proceed to complete the transposition process. And what do we do next? Add the fractions on the left hand side in the usual way. There we have 12 as the common denominator, and then we are adding the fractions in the usual way. We know this way of adding fractions that have what we call exclusive denominator, that is, denominators that do not have common factors. Right. Eliminate 7 by multiplication. So we are just, since we have just done our reciprocal, as a matter of fact we did that a few steps ago, and now we have the sum of the fractions. Now we may do the reciprocal. That is what we are doing. Let us do the reciprocal first, then proceed to complete the transposition process. Add the fractions on the left hand side in the usual fashion. And we know how to add those fractions that we consider to be fractions with exclusive denominators, that is, denominators that do not have common factors. The product will go there, the product of the denominators, that is, will be the common denominator, and then we have 3x plus 4y, and that is equal to the same thing that we have here, t over 7. And as a matter of fact, we are saying that because the proposed subject was initially in the denominator, And for the purpose of transposition, it would be better if it were in the numerator. Therefore, at some stage, if that is our approach, we will have to reciprocate, because there's another way to solve a problem that we will see a little bit later that does not require that we find the reciprocal of any of the fractions. But I'm saying, if that is the approach that we are taking with the intention to find the reciprocal, then we are saying that since t is in the denominator, then at some stage we will have to do the reciprocal. We are also taking a look at what will happen if we find the reciprocal of the fractions first, which is what we consider to be the incorrect way of doing it. So we'll take the step to find the reciprocal first, and then we will add the fractions as we have done before in the usual fashion. Then we will eliminate 7 by multiplication. We need to make t the subject. All that we have here now is that we are dividing by 7. We will eliminate this 7 denominator by multiplying by 7, and that is the result. As a matter of fact, we are not going into much of the detail of the transposition process here, because we are not explaining transposition. We have done that in 3 considerably long tutorial videos. Right here we are demonstrating why it cannot be right, if we are intending to do the reciprocal, to do that irrespective of the fact that we have 3 fractions. I am saying that in order for us to reciprocate and do that correctly, we need to have only 2 fractions, 1 on either side. So that is our result, with the exception that we need to place the subject on the left hand side. There we have it. We are saying that that answer is incorrect. Let us use another method whose legitimacy cannot be refuted to solve the problem and see how the answer compares with the other 2. And when I'm saying the other 2, I mean the one that we know to be the correct one, and also with this one. So we will not do the one that we reciprocate the fractions. We will use another method, and the method that we will use is the one that requires us to multiply by the common denominator. So let us multiply by the common denominator, and we are choosing an expression for our common denominator that x, y, and t can divide into, and we just say that is x, y, t. So let us eliminate all denominators by multiplying the entire equation by x, y, t, and I am sure that this is a universally acceptable or accepted method of eliminating the denominator. That is the one that I am speaking of. That one is irrefutable. So multiply by x, y, t, and we will take a look at that under the microscope by multiplying 4 over x by x, y, t. What will happen? The x's are gone. 4yt. What else? The other fraction. The y's are gone. 3xt. The other fraction. The t's are gone. 7xy. And we put those together, and that is our new equation. And t is our proposed subject. We have 2 occurrences of the proposed subject, and we need to factorize. So use the proposed subject as the common factor in factorizing that left hand side, and all that we do is what we usually do. By analogy, divide by that large factor. quote-unquote large factor. And that's all there is to it. Surely we can see right here that this and this are not the exact same thing. Therefore, this being the answer that we had before, which is the correct answer, and which we are proving to be correct by using a universally accepted method. We have used that universally accepted method to solve the problem, and we receive the same answer as the one before. Therefore, we are sure that this one is correct. Therefore, the other method, which is the one that we use to solve the problem, is also a correct method. This one is definitely an incorrect one. If you can remember, the answer that we have there is the same as the one that we received. We received by first writing the expression as a single fraction before inverting. It therefore means that adding the fraction first is the correct thing. The other answer is not correct, as we said before. And what do we do? Let us dabble a bit with a few digits in order to show in a numerical case that our assertion is correct. Let us find the sum of the expression as it is first. Find the sum of those two fractions first, which is what we said that we needed to do. And we know the method already. Right. And that is 7 over 12. Let us reciprocate now. Therefore, the value of x is 12 over 7. But we are saying let us reciprocate first, which is the incorrect way, and see what happens. What do we have there? 4 plus 3 is equal to x. So x is equal to 7. If by reciprocating x is equal to 7, then this means that the sum of the fractions was equal to 1 over 7. Right, so the sum of the fractions, if when we reciprocated, the answer is 7, that means if x is equal to 7, that means the original, which is this, should be 1 over 7. Why are we saying that? Because if you find the reciprocal of something and it is equal to 7, then the number that you reciprocated to get 1 over 7 has to be 7. Or if you reciprocated a value and you got 7, then what you reciprocated to get 7 has to be 1 over 7. So this setup is claiming that since x is equal to 7, what we had originally, which is 1 over x, was actually 1 over 7. And we are sure that that is not right. Because we know from our work right here that 1 over 4 plus 1 over 3 is not 1 over 7. So we are sure that this is incorrect. We already know that the fractions have a sum of 7 over 12, which reciprocated to give 12 over 7. Therefore, it cannot be correct to invert the fractions first. Therefore, this that we have done, inverting the fractions first, that is incorrect. Because when we did that, we got an answer which is under the assumption, or would be proving, or would be claiming that the original sum of the fraction is 1 over 7. But we know that it is not 1 over 7. Therefore, the claim is incorrect. For sure, if we invert a fraction and invert the result, then we should be back at square 1. So if we invert a fraction and then invert it again, then we should be at square 1. Therefore, if x is equal to 7, then finding the reciprocal should result in 1 over 7. So x, or the reciprocal of x, is equal to 1 over 7. In the second case, when we found the reciprocal and did the reciprocal again, we did not recover the original value. So when we did the reciprocal right here and we got 7, we did the reciprocal again, we got 1 over 7. But at the same time, this 1 over 7 is not equal to the sum of the fractions that we have here, so it is not correct. In the second case, when we found the reciprocal and did the reciprocal again, we did not recover the original value. This tells us that the result of the second attempt is invalid. We will add two fractions of a special kind and take a look at the result. The fractions have a numerator of 1. Let us look at the result. But we know that when we add fractions with exclusive denominators, this is what we will get. So the product will go there, and of course that one and that. Notice that there is a simple relationship between the numbers in the denominator of the original fraction and the numerator and the denominator of the result. So let us take a look at that. There is a relationship between these two, and then these two and these two. And what is that relationship? The numerator of the result is the sum of the original denominators. So we have a plus b in the denominator, and we have a plus b in the numerator, which is the sum of these denominators. The denominator of the result is the product of the original denominators. Therefore, when we add two fractions with each having a numerator of 1, the resulting fraction may be described as sum over product. The sum of the original denominators over the product of the original denominators. Look at a few examples. So we have adding fractions whose numerators are equal to 1. Then we may just find the sum of the denominators and put that over the product of the denominators. There we have 1/3 plus a quarter. What do we have there? The numerator is the sum of 4 and 3. 4 plus 3 is equal to 7. And the denominator is the product of 3 and 4. 3 times 4 is equal to 12. Here again, the same is true. The numerator will be the sum, and the denominator will be the product. And finally, we have the numerator, the sum of 2 and 9. 2 plus 9 is equal to 11. And the denominator is the product of 2 and 9. 2 times 9 is equal to 18. Nice. When we add such fractions in that fashion, we are not taking a shortcut. We are making use of information. As a matter of fact, physicists make use of this fact with a free conscience when they are finding the sum of resistors in parallel. So this has a direct application in the principles of physics. Therefore, we should not consider it to be a horrible shortcut. It is already understood that when we are adding two fractions and their numerators are equal to 1, that the sum may be found by taking the sum of those denominators and write that as the numerator of the result, and then the denominator will be the product of the original denominators. Now here is the $64 million question. Why don't we change the signs when we are reversing an equation? If you argue that the signs should change, then you are correct. If you argue that the signs should not change, then you are also correct. And we are talking about when we have an equation or maybe a formula, and we are finishing up by writing the proposed subject on the left hand side, or we have solved an equation and we are reversing. If we solved an equation for x, we are now writing x on the left hand side. Why is it that we do not have a change in signs? And then we have some saying that there should be a change in signs, and I'm saying that you are both correct. Remember the ad in which the parents were arguing, one saying that Wincarnis is a tonic and the other was arguing that Wincarnis is a wine, and their son had to point it out to them that Wincarnis is in fact a tonic wine. Therefore, if a simple advertisement can demonstrate that two people who look at the same thing from different perspectives can both be correct, then I imagine that mathematicians should not find it as difficult as a goat attempting to swallow a pear seed. An avocado seed should not be very difficult at all. We are saying that 10 is equal to x. This means that the two of them are the same in value. That means they are equal. It should be, well, it should not be so difficult to see that if 10 is equal to x, then x is equal to 10. It would be in defiance of simple logic and common sense not to see that x is equal to 10. There we have it, x is equal to 10. Therefore, the reversal of the equation may be treated as if, effectively, there is no change in sign. But there is. Therefore, I am saying that the end result is as if there is no change in sign. To say that there is no change in sign is therefore not entirely incorrect, because the overall effect is as if there is no change in sign. In this case, the change in signs is analogous to a catalyst in a chemical reaction. The catalyst actually takes part in the reaction, but at the end its original composition is recovered as if it was unaltered. The same is true for the change in signs in this particular case. Therefore, one may argue that there's a change in sign, for sure, but in the end, the effect or the end result is that there is no change in sign, or there appears to be no change in sign. However, if we are reversing an equation by principle, we will see what happens. The other argument is the one that some students imagine. If we are reversing the equation, it is as if we are eliminating x from the right hand side and simultaneously eliminating 10 from the left hand side. Viewed in this way, there is definitely a change in sign. So if we need to eliminate this x from this right hand side, we need to subtract x, and we subtract x from the left hand side also. And if we are eliminating the 10 from the left hand side, we are subtracting 10 from that left hand side and subtracting 10 from the right hand side also. So that will cause negative to appear on both sides. So the reverse process will change both sides, because what we are actually doing is eliminating x from here, which requires that we subtract x, and we are eliminating 10 from here, which requires that we subtract 10. So we will have this situation. We want x and not negative x to be the subject of the formula. We may eliminate that negative sign by multiplying by -1. However, we will have to keep the equation balanced by doing the same on the other side. So, attempting to get a positive x, we will multiply by a -1. Keep the equation balanced by multiplying by -1 on the other side also. On the left hand side, negative times negative is positive, and the same is true on the right hand side, and -10 times a -1 is equal to a positive 10. So x is equal to 10. We could have chosen to divide both sides by -1. The effect would have been the same. Negative divided by negative is positive, and negative divided by negative is positive. As we have discussed before, multiplying or dividing a number by, or expression as a matter of fact, by -1 has the same effect on the value of the number. The effect is to change the sign of the number or expression. So we could have achieved the same thing by dividing both sides by -1. In the end, a half of a dozen is equal to 6, and a cup that is half empty is also half full. One may be looking at the process and saying that there is a change in sign. If you look at the process in graphic details, you are correct, as we have just shown. The other may be looking at the end result and saying that there is no change in sign. You are also correct, because effectively there is no change in sign.